Professor Luc Darnière. We talk about triangulation of semi-algebraic sets over p-adic fields.
Oh, good morning. I would like first to thank the organizers for the kind invitation. It's a great pleasure for me to give this talk in this beautiful place. I will, in this talk, the first part of this talk, I will define all the words of the title, and if time permits, I will try to give some elements of the proof. Well, although probably most of you know at least these few words, recall that just like a real closed field is a field which has the same theory as the field of real numbers, the p-adically closed field is just the field which has the same theory as QP or finite extension of it. Thus, p-adically closed field is not necessarily QP. It can be a finite extension of it, or it can be, for example, the relative algebraic closure of Q inside such field F, which is an example of a p-adically closed field, which is not a complete field and which is countable. It can be also, for example, the p-adic completion of the field of Puiseux series, or finite extension of QP, which gives an example of a natural example of a p-adically closed field whose value group is not Z, but which is larger. Well, probably either you know all this pretty well, or you don't care, and then you can stick to the case of the p-adics, of course, if you like. And for semi-algebraic sets and maps, let me remind the definition. In any field, you can consider the subgroup of the multiplicative group given by all the n's, the non-zero n's powers. A subset of the affine space over K is called algebraic if it is the set of solution of polynomial equations with coefficients in the field. And it is called semi-algebraic if it is a finite union of sets defined by equations and also by conditions like this, where all the F and J are polynomials with coefficients in K. Probably the real geometers won't agree with this definition of semi-algebraic sets, but let me point that if K is algebraically closed, the condition of being an nth power is an empty condition, or exactly to be a non-zero nth power is just to be non-zero. And in the real closed case, to be an nth power is a non-zero nth power is either to be non-zero or to be strictly positive, depending whether n is odd or even. So the above definition is indeed the right definition of the usual definition of semi-algebraic sets in the algebraically closed and in the real closed case too. In the p-adically closed case, we do not have such simplifications, and thus we do have to consider such conditions for various integrals n. And final remark, in any case, since Pn is a subgroup of finite index, it's easy to see that semi-algebraic sets are also stable by Boolean combination. And actually, this is the main difference with the algebraic sets. And finally, let's recall that the map is called semi-algebraic simply if its graph is a semi-algebraic set. So we have these fundamental theorems from Tarski for the real case and McIntyre for the p-adic case, which say that if you take a semi-algebraic set and project it onto subspace, the image of the projection is still a semi-algebraic set. And this can be rephrased by saying that semi-algebraic sets are just what you obtain if you start with algebraic sets and you want to stabilize with Boolean combinations and projections. So even if you're mostly interested in algebraic sets, considering semi-algebraic sets is somewhat natural from this point of view. This can be considered as the foundation of what's the so-called semi-algebraic geometry. Indeed, these geometries are, these structures are Tame, which is shown by the fact that they have a lot of nice properties. So I recall first the context. In the case of real closed fields, you have the so-called Skolem functions, that is, every semi-algebraic map has a section, a semi-algebraic section, sorry. And you have cell decomposition, which, as everybody knows, gives, among other things, a good dimension theory. You also have a classification up to semi-algebraic bijections, simply by means of the dimensions and the Euler characteristic. And you have stratifications, which is a key tool for stratification for singularity theory. And finally, you have a triangulation in the sense that every semi-algebraic set is semi-algebraically homeomorphic to the union of a simplicial complex. The simplicial complex, which is simply a finite set of complexes, of simplexes, sorry, which are disjoint and touch each other only along their faces. This triangulation is allows to define properly the Euler characteristic and can be used to for the above classification, among other things. And let me also recall that all this, as you know, generalizes to minimal expansions of real closed fields, as well as trivializations, for example, and many other things. In the p-adic case, we also have a Tame structure. We have semi-algebraic Skolem functions. We have cell decomposition, thanks to Denef. We have a classification up to definable bijections, thanks to Kluckers, with this interesting difference, which is that in the p-adic case, you do not have Euler characteristic. The classification is simply given by the dimension, except, of course, for the 0 dimension where you have the number of points which counts. But part of this case, it's the dimension is the only real p-adic invariant for definable bijection. You have stratifications by results of Kluckers, Comte, and Löser. And from now on, you have triangulation. And all this, but triangulation generalizes at least to p-adic subanalytic sets, but not to p-minimal expansions of p-adically closed fields, which is the p-adic analogous of O-minimality is p-minimality, but it doesn't work as well as O-minimality, since first of all, you don't have Skolem functions in general p-minimal structures by a result of Kubilis, Kovacic, and Grian. But on the other hand, this is an obstruction, and you can generalize all this but triangulation to a slightly better context, which I introduced with Emilia Lubchak, and which we call p-optimal fields. Anyway, I won't talk about this. I just mentioned that the results that I will present here is really restricted to the semi-algebraic case. I have been unable, although I did a lot of efforts to this, I have been unable to generalize it to, for example, to the subanalytic case. also I'm quite convinced that it is possible. So if there are some voluntaries, you are encouraged to go on. So now, last word of the title that I have to define is triangulation in the p-adic context. So I will first fix p-adic field, a p-adically closed field K, its valuation V, its valuation on R, an element with the smallest strictly positive valuation. From time to time, I will use also this multiplicative notation for the valuation. So it's just the same thing, but the order is reversed. And with this notation, so the addition is replaced by multiplication. So we have properties which are probably, for me at least, more intuitive. And to make things simpler, I will stick to the case of a Z group, of the value group, which being just the usual group Z. So, what are the problems? First problem is that in the real, everything is defined by means of the order. A polytope is a convex hull of a finite set, or it is defined by linear inequalities, and we have no order in the p-adic fields. Well, this is no harm because you have an order on Z value group, so you can consider subsets of the value of the defined space over Z defined by, say, by linear inequalities, and then look at their pre-image via the valuation. So there's no problem with it a priori. Another big problem is that we hope polytopes, some simplexes, to have a nice notion of faces. Everything is based on faces when you're talking about complexes. We need polytopes to have faces, those faces to be themselves polytopes. And the faces of a faces, well, if you take a polytope A, the face B of it, B must be a polytope. The faces of B must themselves be polytopes, and the faces of B must be some among the faces of A. This kind of properties are quite natural, but not non-obvious after all. And especially if you look at subsets of Z to the N, they are Klopen, so there is no face, no topological notion of face. And the solution is quite simple, actually. It's because we don't look really at Z. We look at the image of the field K by the valuation. So we have fortunately one more point, the point at infinity. And this one is enclosure of Z. So this will be, for example, the face of Z. We consider Z as a simplex, which is not because it is not bounded above, but part of this. This is an example of a face of a discrete set. And more generally, well, in order to visualize things, since all the important points, the faces will be at infinity, I will use a compactification, which preserves the order. So here are the points of Z2, and here on the right side are the points whose first coordinate is plus infinity, above the points with second coordinate plus infinity, and here is a single point plus infinity plus infinity. And the notion of faces appear quite well on this picture, I think. In order to formalize it, I'll call the support of a point A the set of indexes with finite coordinates. And I will denote by F index I of gamma Q the set of point of gamma Q with support I, and Pi I the projection onto Fi. So for example, here you have this is f index 1, 2, since all the points have support 1, 2, both coordinates are finite. The points here have so their first coordinate, which is finite, so they form f1, f empty, f2, so that it's clear. And the projection work like this. So we have now a notion of phase, at least in gamma Q, and you can observe that the phases form a complex. They touch each other along their own faces. If one considers now a subset, any subset of gamma Q, I will denote by Fi of A the intersection of the closure of A with the corresponding face of gamma Q. For example, here you have, no, it's here. You have something which will indeed be a simplex. It is defined by linear inequalities, as you see, and it has one face set, that is one maximal face, and another smaller face on the top. And here you and here okay, and here you have also another subset defined by linear equations. Well, it is defined by linear equations, but due to the compactification, the lines are curved. Okay, but well, this is no harm, and you can observe that this thing, which looks two-dimensional, has only one facet, which is zero-dimensional. So you have a notion of faces, but it doesn't work completely like in the real case. But you do have good properties if you take if you take a subset defined by conjunction of linear inequalities, then, for example, you look at two faces always intersect somewhere on along another face. The faces of the faces are faces of the initial subset, and moreover, each face is actually the image of the subset A by projection. As you can see again in this picture, this set has three proper faces, and all of them, the faces of the faces are faces, and each face is actually the projection of the set A onto the corresponding face in gamma Q. So this is pretty nice, but there is a problem. Guess what? The problem is the following. Look, for example, at this set. Well, I should have defined it simpler. It is defined simply by this and this. So it is indeed defined by linear inequalities, and it has a face at infinity, face with support 3. That is, you look at this equation, you fix t, a finite t, and you take some points satisfying this equation, and you make x and y tend to infinity. You can do this with x and y, with this difference you can make x and y tend to infinity while still satisfying this equation, provided t is even, only if t is even. And for this reason, the face that you get here, the support 3, is made of even positive numbers. And thus, it is not defined by linear inequalities. So if you want to define polytopes by linear inequalities, the notion of face that I have just introduced, which seems quite nice, has a defect. The faces of such an object defined by linear inequalities is not defined by linear inequalities. So what is the solution? Well, the first solution is you can weaken a little bit your ambition and consider now subsets of z to the q defined by linear inequalities and some congruence conditions, which is the so-called Presburger sets or definable sets in logic. But then this proposition won't apply, and most of these properties will be lost. So you are stuck. So you have to find something else, and this is the right definition of discrete simplexes. I will say that a map is strongly continuous if it can be continuously extended to the closure of its domain. And I will define a discrete polytope in a way which is very close to what is called cells in the domain. Discrete cells or Presburger cells have been introduced by Klucker, and I have reused this definition with more assumptions. So a discrete polytope, it is defined by induction. First, a point is a discrete polytope. And once you have defined polytope on Z2, say, you will consider as a polytope in Z3 something which is defined by, well, how could I draw it? You can imagine two planes, and you take the region which is limited by these two planes. So this is the sense of these two inequalities here. T is between two functions, which are linear functions. The point is that we require these linear functions which to be non-negative and strongly continuous Q-linear maps, or also they can be constantly equal to plus infinity, in which case you are on the top of the cube. And with and this is for discrete polytopes in Z to the Q, but of course, when you are on the border of the cube, for example, this side here, you can identify it by Z2 and take the same definition. So in the preceding example, the set A, which was not a simplex, was defined just by its definition had exactly the same shape. That is, its basis was defined by linear equations. On itself, it was defined by this such pair of conditions. But the point was that precisely these functions, these two same function 2y minus 2x, was not strongly continuous. It has no limit at the point infinity, infinity. So note also that since, so this is a very special kind of sets defined by linear inequalities, and it is also a very special kind of cells, actually. But anyway, since it is defined by linear inequalities, the proposition here holds true for all the polytopes. What we have in addition is that if you look at a polytope, it is quite easy to see that when you are going to the side of the polytope, so imagine that you have something which is bounded by two linear functions. When you go to infinity, since these linear functions are strongly continuous, they extend to functions here, and the face it's difficult to represent it in 3D, but here you will still have something which is bounded by two functions. So it will take more or less the same shape. The problem, the only thing that we have to check is that these functions are still Q-linear. There is no reason a priori for that, but it's true. And another things I want to mention is that actually, in this proposition, everything is trivial. I mean, to pass from this is just taking the limit. So what is not trivial is this. It is the fact that if you are looking at, start from A, you look at its face B, here you have the circle of A, it has also a face here. And the point is that the circle of the face is the face of the circle. And this is not trivial, but it was. So why are this extension mu bar and nu bar Q-linear? It's because of this dichotomy proposition, which says that if you have a function, if you have a set X defined by linear inequalities, and you look at the face of it, and if you have, if the function f extends continuously to y, well, actually, f on x is entirely determined by its restriction to y. That is, if y here takes at least one infinite value, then f is constantly equal to plus infinity on y, and then f is not determined, as contrary to what I've just said, by its limit here. But on the other hand, if here f never takes value plus infinity, then it is Q-linear, this on this part, and f is simply the compositum of this restriction by the projection. Thus, f is, in that case, entirely determined on x by its values on y, which proves that the notion of simplex that we are considering is actually pretty rigid. And the obvious corollary is then that the faces of any discrete polytope is again the discrete polytopes. The maps mu bar and nu bar that we considered before are indeed either plus infinity or Q-linear, thanks to the dichotomy theorem. So now you know what is a discrete polytope, and it still remains to define what is a discrete simplex. In the real case, there is a characterization of the simplex, which is not very well known, and I didn't know it before, but which is not in terms of, you can define the simplex as the convex hull of unaffine basis, something like that. Again, we don't want to avoid convex hulls. So there is another characterization, namely that the simplex is, among the polytopes of the same dimension, the one which has the least possible number of facets, of maximal faces. And in the p-adic case, simplex can have only one facet. This is the least possible number of facets, except that it can also have 0 faces. It can be Klopen. So I will define a simplex as a discrete polytope which has only one facet, which itself has only one facet, and so on. So all the faces of a discrete polytope are linearly ordered with the order specialization, the specialization order. So this is a simplex, and this is another one. Okay. So we have seen already that our polytopes and simplexes have nice properties, and I would like to mention one more property which is important in the proof. In this, well, the first thing is that, well, everybody knows that on the reals, any polytope can be divided in simplexes, of course, in such a way that this is a simplicial complex, which refines the initial complex made of the square and its faces. This can be done also in the discrete case, and even more can be done. In the real case, you have a certain tool called Barycentric Division, which means that not only you can divide a polytope in a simplicial complex, but you can do it while respecting a certain amount of constraints, which you can do it very freely, in a sense. I won't give, instead of giving a formal proposition of what is this monotopic division, I just give a loose idea. So consider this polytope and consider simplicial complex which refines the complex of the faces of the polytope, of the proper faces of this polytope. Then also consider, this is a constraint, a certain neighborhood here of the border. Then you can find a simplicial complex which refines the given complex on the border. That is, this new simplicial complex has, well, in the p-adic, it's here, it has no faces, it is open. The faces of the various simplexes which occur here are either empty or are among the simplexes which were initially given on the border. And moreover, the simplexes which touch the border are always contained inside the neighborhood that I have fixed. It is, as you see, a tool of division which can satisfy a lot of conditions, some of which will play a key role in the triangulation, in the proof of the triangulation theorem. So it's time now to introduce p-adic simplexes. I say that we could, at first glance, consider the inverse image through the valuation of discrete simplexes. But actually, a little bit more must be done. We have to introduce this, this set Q and M star, which I have represented here. It's a union of balls centered at the power of pi. It is a neighborhood, actually, of this set of power of pi's. And it is a definable neighborhood, a semi-algebraic neighborhood, sorry. And it is also a subgroup of the multiplicative group with finite index. I did not introduce this. It is something which has been more or less introduced by Denef and made me more precise by Kluckers. So p-adic polytopes and simplexes will simply be the inverse images of discrete polytopes and simplexes intersected with these multiplicative subgroups of Q, K star. And they inherit from their discrete ancestors all their nice properties regarding faces, monotopic division, and so on. Now, as usual, the p-adic simplicial complex will be a finite family of simplexes which touch them only along their faces, but there is a little twist here. Indeed, in the real case, you do your triangulation in an ambient space whose dimension is preserved. That is, if you have a semi-algebraic set in R3, your simplicial complex will live in R3 too. Not in the p-adic case. The dimension of the ambient space can grow up, and we have to consider actually disjoint copies of a fine space, and hence in which the simplexes that we are considering are living. This is no harm, but it's a little difference. So a simplicial complex in the p-adic case is actually a finite family of simplexes and so on, but living in possibly disjoint copies of R to the n or R to the q. And with this definition, we can finally set the theorem, which is that there is indeed a triangulation, which works pretty well. Every semi-algebraic set is semi-algebraically homeomorphic to the disjoint union of a simplicial complex. And you have some preparation on functions defined of such a set, semi-algebraic functions, of course. which says that if you take such function theta I, the compositum with homeomorphism will be a function whose valuation is a z-linear function in the variable in the simplex. That is, you have your set X, you have a function theta, you have a triangulation phi, and if you look at theta phi on such a simplex, and you look at the valuation of this, this is a z-linear map on the valuations of the coordinates of the points here. We can't say it multiplicatively. It's something like theta composite phi is a monomial. Actually, it is not. There are some things which are lost by the valuation, but it is almost monomial. And I will make it precise very soon, as soon as possible. A first application of this, an immediate consequence, is that the number of homeomorphism classes of semi-algebraic sets over K is simply the cardinality of the value group, because there are no more semi-algebraic sets up to homeomorphism than there are simplicial complexes. And simplicial complexes are finite set of simplexes, and simplexes are defined in terms of Q linear maps plus one constant value in the value group. So there are no more simplicial complex than elements in the value group. Let me give at least two applications to semi-algebraic geometry of this triangulation in order to motivate this a little bit. First, let me recall that the retraction is a continuous map. Well, it's just what you think. This, no, you move something from A onto B without moving B pointwise. And such a retraction not always exists. For example, in the real case, if you are looking to a disk, you cannot restrict it to a circle because there is one point that is missing, that we will not know where to send. This kind of obstruction in the real case is controlled by a homotopy. But in the p-adic case, there is nothing like a homotopy. It doesn't work, so there is no obstruction a priori. In fact, that there is no obstruction is not proof that there exist retractions, but indeed, there do exist retractions whenever it is possible, that is, whenever B is relatively close in A. And an immediate consequence of this is that if you have a function, continuous function defined on some B which is closed in A, you can extend it to a function, a continuous function on A, on the wall of A, simply by taking F, the retraction composed by F. That's true. These two results were obtained previously by Kluckers and Martin with different methods. They didn't use triangulation. And the result is more general in the sense that they proved it in the subanalytic case too. But it is less general, it is weaker in the sense that they only prove it when the set A is the whole space K to the M. And apparently their argument doesn't extend to this general case. So, sketch of the proof. By means of triangulation, starting from A and B, you reduce to the case where A is a simplex and B is a face of it. Or A is a simplex and B is A, in which case there is the restriction, the retraction, retraction is just the identity map. So there is nothing to do. And if B is a face of A, there is nothing to do either because you have a projection. It is our first property. The faces are the image of A by projection, by the coordinate projection. So that's it. Second application, splitting theorem. This is a little bit more complicated. You are looking at a semi-algebraic set A, and you are looking at some closed, relatively closed. Well, maybe I'll try. So you have a semi-algebraic set with a frontier, and you are looking to some sets which are closed and cover all the frontier of A. And then the theorem says that you can divide A into pieces which are open in A and whose frontier is just the two sets which are given here. This is absolutely impossible to do it in the real. It implies non-connexity, for example, but it is a very, very, very strong form of non-connexity. You not only divide in two Klopen sets, it's much more than this. Divide in Klopen sets, Klopen in A, but in such a way that you control exactly the frontier of the different pieces. Very sketchy proof. Again, you reduce to the case of where A is a simplex, and the xi's are either A itself, and there is nothing to do. No, they are not A itself since they are in the frontier. Sorry, the xi's are union of some proper faces of A, and since they cover all of A, actually at least one of them, x1 or x2, must contain the largest face, the facet of A, and hence x1 must be equal to the closure of the facet. So you have two cases. So you have first that you have S, you have its facet T, you have T1, which is T, and you have T2, which is a face of T, which can either be T itself or some proper face. If T1 is T2, you want to divide S in two pieces with frontier T1 or the closure of T1 or the closure of T. So that's easy. You just take the points with odd coordinates on one hand and the points with even coordinates on the other hand. Of course, you can't do this in the reals, but in the p-adics you can. And this makes the division in this makes a job in, for example, in this case, this is A, this is B, and you divide B in two pieces, which are the points whose first coordinate is odd or is even. Well, this is when T1 equals T2, and the other case is a bit more complicated, and I won't go into details, but intuitively it's clear that if you have something like that, so here you have T, which is T1, here you have T2, well, you just have to cut it to divide it like this. A1 we have frontier T1, on the A2 we'll have frontier only T2. So that works. You can use also the monotypic division. It is actually a special case. Well, how much time left? 0. Okay. So I of course I won't go into the proof. But I just want to state at least the triangulation theorem in a more precise way, since actually it's a bit stronger than what I've presented. And okay, I'll remove this. Well, let U index E denotes E's power of 1, and U index E n be a neighborhood of EU, which is made of both central as point of EU. And I will say that the function is n monomial if it is a monomial with exponents which are multiples of n. And it is n monomial modulo this group if it is n monomial times a constant times some semi-algebraic function which takes value in the above defined neighborhood of the group. All right. So this is not n monomial, of course, but it is in some sense close to be so. In which sense is it? But actually, it means that if you this is true if and only if can find so f is n monomial if and only if you can find an n monomial function and a function with values in the eth root of 1, such that the product here, the quotient here, -1, is small. That is a kind of multiplicative approximation of f by an n monomial function times something like a character. And the triangulation can be stated more precisely in that way. That is, you take again semi-algebraic functions on some set, and there is a p-adic simplicial complex and a semi-algebraic homeomorphism from the union of this simplicial complex to X, such that each function theta after composition by the homeomorphism becomes n monomial modulo UEN. And you have some, you can make n as large as you want. There are some things, some nice little things that you can do. The proof goes by induction on M. If I call Tm this statement, so M is a dimension of the Riemann space. And since it goes by induction, you can imagine that cells will play a central role. We prove things on the bottom, and then we go up by induction using the fact that we have some cell decomposition. So the triangulation, the proof of triangulation is based on cell decomposition. But I suppose that I have to stop here.